All right. Well, good morning. So up to this point, we've expanded our discussion. We went through vibrational spectroscopy, rotational, and row vibrational, and we had a test on that. Then we got into the electronic structure of the atom. So we built up the atomic orbitals. We learned about the quantum numbers and so on. We looked at the atomic spectroscopy of the atoms, specifically the spin-orbit coupling that gave us kind of a fingerprint for each atom. And that's how we know the composition of stars and things like that, or our drinking water. So atomic emission spectroscopy is the spectroscopy of this single atom. And we can see in our tube lights, the mercury atomic spectrum. So if we get a spectrum of this tube light, we immediately know there's mercury in that tube light because of the pattern that we see in the atomic spectroscopy, emission spectroscopy. And that's a pretty simple spectrum. Even though you have all these term symbols and everything, it's understandable. You can build out the electron configuration, and you can draw the term symbols and the J splittings, and you can understand what the individual electron's doing when it absorbs light or emits light, when it's going from level to level. Now we're going to make molecules, and it gets too complicated to follow, really. We're going to spend the last fifth of the course after this exam trying to understand the molecular orbital. And we can understand that to some degree, but it gets so complicated we need a computer to help us. Okay. For the atoms, we can still do it by hand, but when we start making molecules, the electron cloud gets so complicated that we really have a hard time following what's going on. Okay. So that's what we're going to talk about today. We're going to make our first molecules today. We're going to make a diatomic molecule and think about the electron cloud and what's happening with that. And then we're going to just say, from this perspective, we're going to go into drawing the energy level diagram called the Jablonski diagram, where we really don't understand the individual energy levels. We just have bands of energy levels. Those bands of levels contain all of the vibrational levels for the molecule, all the rotational levels. And so it's such a dense forest of energy levels that we don't even think about the individual quantum numbers anymore. Okay, so that's where we're going today. We're going to connect that atomic energy levels to make a molecule, and that simple molecule gets really complicated. So this is the oxygen atom. This is the Grotrian diagram for oxygen. And just, again, a single atom can be pretty complicated. Once we start making molecules with this, it gets ridiculous. So if we zoom in on this bottom level down here, we see we see down here the hyperspine splitting with the J values and the ground state electron configuration. And then we have this next level up there. If we zoom in on both of those, this one up here, this is the output from Gaussian. You see how it's been populated. So it has 2 electrons in the 1s orbital. The nice thing about Gaussian is it gives us the energies of those orbitals here. And so you can see that it's 1s2. Everybody understand that? Yeah. Then you have the 2s orbital, also its energy here. So 2s2, and then this has 2px has 2 electrons in it, and 2py has 2 electrons in it. And then the 2pz is empty. Now, remember we said for oxygen, we would fill up the individual X, Y, and Z first with, say, a spin up, and then we would start pairing them up. And that would be the lower energy configuration. And sure enough, that's what we have down here. So we had the 1s2 here. We got that, the 2s2, and then the 2p, we have spin up, spin up, spin up. So X, Y, and Z all have an electron in them. And then we start pairing it up, and then the 2px has 1, so 1 extra spin down. So then it would be this diagram here. If we were to draw this, it would be the 1s spin up down, the 2s up down, and then the 2p, we would fill them like this. Spin up, spin up, spin up, and then we would pair one up. And so that would be oxygen. That's the ground state electron configuration for oxygen. And sure enough, in the Grotrian diagram, that's what we see. We can go into Gaussian and we can calculate the energies of those orbitals. But there are other ways to put that atom together. This other configuration where we have the 1s up and down, the 2s fully filled, and then the 2p. This one up here has got them paired up in an empty one, and that's higher in energy. quite a bit higher. In fact, it's 16,000 wave numbers higher. So that's almost a visible transition between these two types of oxygen. So then we bring these oxygen atoms together, we get the molecule, so diatomic oxygen. So this is the oxygen or O2 potential energy diagram. So we have that ground state electron configuration. If we combine two oxygen atoms in the ground state, then they can form molecular orbitals. And like I said, our last fifth of the course is generating this picture here. So these are the energy states for the molecular orbital, and we're going to learn how to do that. You've probably run into that a little bit. It is taught, like there's one section in the freshman book on it. So I don't know if your professor taught you that or not, but there's a chance in the freshman course you got introduced to molecular orbital theory. They talk about molecular orbitals in organic. I don't know how much detail you go into in terms of how to build this, but we're going to go into great detail on how to build the molecular orbitals. So that's the last fifth of this course. But for now, this is just sort of foreshadowing. You bring the two atoms together and the energy levels combined, and you get the molecular orbitals. And then that's going to be this ground electronic potential. So this green level corresponds to this green molecular orbital configuration. Now for diatomics, you can kind of write this out in terms of sigma bonds and pi bonds. And so you can say for the first sigma bond, there's 2 electrons, and the first sigma star, the antibonding orbital, there's 2 electrons, and so on. And so some people try to write electron configurations for molecules, and it can be done for diatomics, but that's it. You're not going to get one for CO2. You're not going to get one for water. So I don't teach this at all because it's only useful for diatomics. So I don't think I think that use case is so narrow, why even bother, right? So this is what you can find in some books. Okay, great. But notice how we've got this curve here. This is the vibrational energy level. This is the potential energy surface. Notice how the energy changes with bond length. So what's happening with bond length? Why does the energy change? Well, when we stretch the molecule, the atomic orbital overlap changes. And it's the overlap of those atomic orbitals that make the molecular orbitals, and the energetics change. So there's a sweet spot at the minimum of that potential. That's the lowest energy that molecule can get at that bond length. So it's the electron cloud, when they start overlapping, that the electrons can get between the nuclei and stabilize their position in space. So the electrons flow towards each other, they repel each other, they flow back, and they get into this oscillatory pattern where they start to make molecular orbitals. And then that brings the nuclei together. If the nuclei get too close, they start to repel. And so when the bond distance is shorter than this equilibrium bond length, then the nuclei are starting to see each other and starting to repel each other. So that's where we set up this vibrational potential. It's the electron cloud that stabilizes these two positive nuclei. They don't really want to be next to each other, but they're surrounded by the electron cloud, and that electron cloud can form resonances, molecular orbitals, that stabilize the whole molecule. Now, it's very sensitive to whether the electrons are spin up, spin down, or whatever. And so you can change the whole potential energy surface if you just move the electrons around. So if you have a slightly different electron configuration, then you get a different potential because it's the electron cloud that's holding the molecule together. So if you look at the specific name of or type of software that Gaussian, you learned Gaussian in the lab, that's called an electronic structure calculation. So we guess at the positions and so on of the nuclei using our Lewis dot structures, our Vesper shapes. We come up with sp3 hybrids and everything like that, and we make methane. Okay, but those little sticks on there really aren't they don't exist. These little stick bonds. That's just the equilibrium position of all the nuclei, and it's the electron cloud and the molecular orbitals that hold that molecule together. So Gaussian's calculating the structure of the electron cloud. That's why it's an electronic structure calculation. And if you change the electronic structure, you change the potential energy surface, which also changes the equilibrium bond lengths. So it's changing the geometry. So if you can calculate the electron cloud, you can calculate the geometry. we could put this molecule again a separate way. So this is a triplet oxygen. That's singlet oxygen. And you see it has quite a bit higher energy, different bond length, and so on. Okay. You could even excite one of those molecules up there, and you get even a weaker bond. The depth of this well is the strength of the bond, because if you want to get it out of that well, you have to put in more energy. So you hit it with more energy, you can get it out of that well. If it's a really deep well, you've got a really strong bond. Then this upper one here, this is, you've excited one from the, like even a lower level and put it in an upper level. And this actually dissociates to a different oxygen. These 4 potential energy surfaces all dissociate to ground state oxygen, that lower Jablonski diagram oxygen. That upper one, the red one, it dissociates to that oxygen we just looked at on the Grotrian diagram. So there's 16,000 wave numbers between those 2 flat portions of those curves, the difference between the oxygens. You're going to use that kind of concept with the iodine lab. So the iodine lab, you're looking at spectroscopy that goes from the ground state iodine here, and it hits the wall of this potential up here and works its way down. And so this is the B state and the X state, and that's going to be the connection in your iodine lab. Even though this is oxygen, iodine looks very similar. And so when you get to the iodine lab, this is kind of a foreshadowing of that. Okay, so let's think about these excited states. If we have spectroscopy and we hit this molecule with light, the electrons are in visible light, visible in UV. The electrons are absorbing the light. So they're jumping up to these excited states. What happens after that? Well, you can have internal conversion. Notice all of these are called potential energy curves for diatomic, but for polyatomic or larger molecules, we call it a potential energy surface. And so you'll hear me say that all the time, a PES or a potential energy surface. And so when we excite an electron to an excited state, we excite the electron cloud, what can happen? That molecule can relax along that same potential energy surface, or it can cross over to another potential energy surface. Now, if we have paired electrons in the ground state, let me do this, and we excite one up and they're still paired, it's still a singlet, even though those electrons aren't in the same energy level. Singlet and triplet are talking about whether the electrons are unpaired or paired. If they're still paired, it doesn't count if they're, it doesn't have to be in the same energy level. So if I excite this electron up here or up here, and they're still spin up and spin down, it's still a singlet. And so then the molecule can relax, and if it moves from one potential energy surface to another one of the same multiplicity, we call that internal conversion. So these are some vocabulary words that you need to know. There's a different possibility. If we have a singlet molecule and we excite it and it's still spin paired, and then the molecule starts to relax because we've excited the electron cloud, and that spin flips, either one flips, then we've moved to a different multiplicity. So now we've got a triplet molecule. We had a singlet molecule, now we have a triplet molecule, and that will have a whole different set of potential energy surfaces. So we have potential energy surfaces that are for singlets and ones that are for triplets. We saw that in the oxygen one here. We see this is a triplet potential energy surface. You see this little 3 here. And this one is a singlet. See, it's spin paired. Everything's paired up. So that's a singlet potential energy surface. And so if the molecule in relaxing moves from one of these singlets to a triplet, that's intersystem crossing. And if it stays a singlet, like this dark blue one, that's a singlet. This light blue one's a singlet. It can move from this dark blue one to this light blue one, and they're the same multiplicity. And so that would be called internal conversion. And then the molecule can move to one that's not bound and dissociate. Okay, so we give the electron enough energy that now the bond breaks. So that can happen. You hit it with enough light, it excites the molecule, and the atoms can move far apart and break the bond. And then there's well, we'll see examples of this. Then you have pre-dissociation, and we'll look at dissociation versus pre-dissociation. You really can't understand that one without a picture. And then also we have radiative decay, where you just have the electron jump back down to the ground state and spit out a photon of light. Now, if the multiplicity does not change, then that's fluorescence. But if the multiplicity does change, that's phosphorescence. So this might be singlet to singlet emission. It could also be triplet to triplet. But the point is, for fluorescence, the spin pairing doesn't change. Okay. This one up here would be like triplet to singlet or singlet to triplet, where you do have this less statistically favored emission and a spin flip at the same time. Since this top one is not allowed, it's forbidden, it takes longer to happen. So a lot of these rules are forbidden, like by symmetry and so on, and that only applies if you have a perfectly symmetric situation. You have something that breaks that symmetry, all of a sudden it's allowed. So the molecule is sitting in this excited state. It can't emit light until some statistical condition happens, and then it leaks out, like it jumps down. Okay, it's just less probable that you'd have a spin flip and an emission at the same time. So it still happens, but it takes a lot longer for those conditions to arrive. And this is where all of your glow-in-the-dark stuff happens. Okay, so you charge up these phosphorescent molecules with light. You're getting all of these electrons in the excited state for this molecule. So it's in an excited state, and it would emit light in the right conditions. And so statistically, it waits longer for that to happen. And so then you take this charged up object into the dark and it glows. It's emitting light over time and has a lot longer lifetime. And so that's what we're trying to show here. This is the time axis. And so we have the illumination on, so we're charging up the substance. If the molecule can emit light without flipping a spin, then it fluoresces. You turn the light off, and it does emit light after the light is off, but it happens so fast it's hard to see sometimes. Okay, so you turn the light off, and maybe it glows for a few, like 10 to the -8 seconds or something like that. You wouldn't really notice. I mean, you could notice it with a spectrometer, but you wouldn't really notice with your eye. But the phosphorescence, you turn the light off, and it glows for a long time. It can be seconds to minutes that this thing can glow. So that's where the glow-in-the-dark stuff comes. Those are phosphorescent compounds that are in those glow-in-the-dark Halloween decorations. So this is, when the illumination is on, we're just blasting electrons up into the upper states. And so the way I think of this is the pachinko parlor game. And I've got this, I found a video of it. And so this is the pachinko game. And it should play here. Yeah, there it goes. You gotta have the sound. It's one of the loudest things ever. This doesn't do it justice. See, the person's hitting the handle and shooting the balls up at the top, and they're bouncing through all of the energy levels. Okay, I'll play it again. Oh, go back. Okay. Now, this little gap right here. Oh, see, it got some, and it gives you more balls. So this is the sort of the phosphorescent hole here, and notice how it's not very common that it'll happen, okay? But it does happen, okay? And that would be if the molecular structure sort of forces it to be phosphorescent, okay? So most of the molecules have these non-radiative relaxation pathways. So when it's bouncing around through all of these little pegs, it's giving off tiny little photons of light that are in the infrared. But we're using, for this particular electronic spectroscopy, we're typically using a visible spectrometer. And so we wouldn't see the infrared emission that comes out of these molecules. So we call that non-radiative. Okay, technically that's not true. It's giving off infrared light, but we're looking in the visible region, so we don't see fluorescence or phosphorescence, so we call those things non-radiative. Does everybody understand that? Yeah, if it's giving off its energy through these pegs, these tiny little energy differences, those are in the infrared. But if it gives off a visible flash of light, it's fluorescence or phosphorescence, we would call that a radiative transition. So let's go through all of these different fates of excited states with potential energy surface diagrams. So here we have absorption. So the light is on, it's illuminating the system. It's throwing the electrons up into the upper states of the electron cloud. So we're on a different potential energy surface. And so this non-radiative relaxation is what I'm talking about. Those are the little pegs in the pachinko game. It's rattling down through the vibrational levels and giving off little infrared photons, but those aren't visible in the visible spectrum, so we call them non-radiative, and it's relaxing. It's going down in energy, so we call that relaxation. If it gets to the bottom of that potential energy surface up here, it stops for just a nanosecond, okay? And then it can fluoresce, and it can give off visible radiation, so we would call that fluorescence. So this would be this setup for a fluorescent molecule. That IR we classify as heat, so it does warm up, but we don't see any visible light coming out of that. Now we might have intersystem crossing. So look here, we've got three potential energy surfaces. They're labeled singlet, triplet, and singlet. And so we shoot that electron up. The molecule is now in this singlet excited state. And right here, notice there's some vibrational energy levels that match. And that appears to be the requirement that favors these transitions. So it's in a singlet potential energy surface. It starts to relax. And there's a situation where vibrationally, it might be in either one of those, and so it can make the transition. So when it's in a vibrational energy level that's the same for a singlet or a triplet potential energy surface, it can switch over to the triplet. Now think about these energy levels. So the molecule is, you can think of them kind of as the molecule is oscillating between these two turning points. So it's going back and forth very quickly, okay? And then it drops down, and now it's oscillating between these two endpoints, okay? And so the atoms are relaxing. They're getting closer together because the electron cloud is drawing them together. And then here it gets to this one, and instead of turning around at this endpoint, it goes all the way out here. And now it's in the triplet state. And so now its turning points are on the triplet state energy diagram. And it's giving off photons and relaxing, and it can go even further down than it would if it stayed on the singlet state.
So it can just kind of go off the rails?
Yeah, it goes off the rails of the singlet state and finds itself on the triplet energy surface. Yeah, and so it's the vibrational manifold that's allowing it to hop from one to the other. And when it does that, then now it's spin flip. So it's starting to move out, and one of those electrons decides to go, nah, I'm going to flip, and it flips, and now it's on the triplet potential energy surface. And we've gone singlet to triplet. Those are two different systems. That's why we call this intersystem crossing. So that's the word that you want to clue in on to keep these straight. We're switching systems. We're going from a singlet surface to a triplet surface. So that's how I keep track of it, because there's internal conversion and there's intersystem crossing. So intersystem crossing is when we have a spin flip and you're now on a new potential energy surface with a different multiplicity. And again, this regular old fluorescence is real fast, and the phosphorescence, this spin flip and emission is forbidden, so it takes longer. Okay, let's talk about dissociation versus predissociation. You know, if we give the electron enough energy, let's say we hit up here on this potential energy curve, you can think of that as putting a ball on this curve. Is that ball going to get caught in the well? No. If you drop a ball in that area on the curve, it's going to go down and roll back up and go out, right? That's the way I see it. So we put the molecule up on a potential energy surface. If we're up above the dissociation limit, it's going to just have enough energy to break the bond. Okay, but if we excite a molecule to right here, it's going to go back and forth between these two turning points. It's going to, like a pendulum, it'll swing down, stop, swing down, stop. Okay, it'll be bound, and so we would have those individual vibrational levels seen in the absorption spectrum. So what's being drawn horizontally on here would be the absorption spectrum and what it looks like. So notice these vibrational levels correspond to peaks in the absorption spectrum. So let me turn sideways here and write wavelength is increasing in this direction. Boy, that's a terrible arrow. God, that's so ugly. I'm going to erase it. Okay. How do I draw a lambda sideways? Let's see. I'm gonna beat this. Okay. Here's my lambda. Okay, that's not too bad. And here's my arrow. And this is absorption right here. So we've kind of drawn that absorption spectrum on its side to show that when I hit this, here's the ground state. When light, hits this energy level difference, you have a peak. And then in between, it really doesn't line up with any levels. And then we hit this energy level and have another peak. And then there's kind of drops off. And then we hit this level and there's a peak. So you see every one of those bumps in the absorption spectrum is a vibrational transition and an electronic transition. And so we would call this spectrum. You remember we had rotation and vibration, and when we combined those, it was row vibrational transitions. This is electronic and vibration. So we call this vibronic. It's crazy. So it's vibration, plus electronic. And so we can use absorption spectroscopy to determine what the dissociation limit is for a molecule, because the vibronic transitions stop and it just becomes a continuum where it'll absorb light at any wavelength without any preference. So the little peaks, the little humps disappear. And when they disappear, you're above the dissociation limit. Because now light of any wavelength can be absorbed, and I can be anywhere on this wall of this potential energy surface, and I have enough energy then to dissociate the molecule. So I don't have any vibrational levels that I'm hitting. Okay, so then there's certain situations where you have, say, a potential energy surface that's unbound. Meaning this one just goes out. If I end up on this potential energy surface, the molecule just falls apart. And wherever those two energy surfaces touch, we lose these vibronic fine structures. So we have some vibronic peaks here, then they go away for a little bit, and then we have some vibronic peaks here. Now, the reason we show this is because this is a tool that we use to find out where the potential energy surfaces are in the electron cloud and so on. So I'm just showing you this vocabulary of pre-dissociation is a tool that we use to map out the bonds in the electron cloud for particular molecules. Okay, so those missing vibronic transitions tell us that pre-dissociation is happening in the system on the right. Okay, now this is much more universal. So this one you need to really pay attention to. And I think this is on the homework, and I think I've given this one in the past on exams. Okay, so the absorption tells us about the upper state. So this green curve here, here's the green ground state wave function in the ground state electronic potential energy surface. So when I'm doing absorption spectroscopy, I'm hitting it with light, and the light is represented by different lengths of arrows in the energy level diagram. Because remember, an absorption line is a difference in energy levels. Okay. All of these arrows start down here at the same energy level. They start at the ground state, vibrational and ground state electronic. So the only difference in the absorption spectrum is the lengths of the arrows that are hitting the upper state. Does that make sense to you? There's a peak here in this green spectrum. Every one of these vibronic transitions are vibronic transitions in the upper electronic state. So if we want to know information about the upper electronic state, we can do absorption spectroscopy. And that's what we will have in the iodine lab. We're doing absorption spectroscopy, so we get a lot of information about the excited state for iodine and very little information about the ground state iodine. Because absorption, the different lengths of arrows, are all different lengths because of where we're going, not from where we started. Okay. If we could get emission spectroscopy, we have radiationless decay, we end up in that red state, and then the fluorescence arrows are all different lengths because they're hitting different levels in the ground state. And so all of these vibronic transitions are characteristic of the lower state. It's kind of getting chopped off here. Characteristic, I'll put IC in there, of the lower state. Another thing, look at the absorption arrow. It's longer, right? The absorption arrow is longer. Long arrow. Okay. So that means this is short wavelength. The radiation, the fluorescence, is a short arrow. And so those are long wavelengths. So fluorescence is always red shifted from the absorption. So this is the excitation curve. This is the emission curve. You see how the emission curve is always to the red of the excitation. This is super important for forensics. So if you're a forensic chemistry major, when we talk about alternate light sources, this is why that works. Okay, we come into a crime scene with a blue or green light, and we put orange glasses on. So we can't see the blue or green light. We only see the fluorescing signal. So if we can take our source of light, if we just draw a line right here with filters, and this is the excitation, and then this side is the detection, and we put our goggles on here, and so we have a filter that blocks the excitation. I know you can't read that, it's text on text, but this says goggles or filter. And so we're only looking on the detection side. So we come in with a crime scene laser, a UV light, a blue light, or green light, and we put on orange glasses. The room is dark. I can't see the excitation beam unless there's fluorescence. Okay, and that's how alternate light source works. And it banks on this right here. I have long arrows, which is short wavelengths for the absorption. So I'm pumping up all of the molecules in the room, and only the fluorescent ones will give me radiation. Everything else is dark. Okay, so I'm looking around and I see, like a bodily fluid here. Boom, it's fluorescing because of the, proteins. Really, there's some fluorescent R groups, and so those fluorescent R groups tell me there's a bodily fluid there that contains the proteins. So I can look around and I can see wherever there's protein, it just lights up. Okay. And it's because of the potential energy surface diagram. The absorption arrow is longer than the emission arrow. And the shorter emission arrow means it's a longer wavelength. And so I can just build a filter, use goggles and filters on my camera, and I can look around and I can find evidence that way. So this is the whole reason why alternate light sources work. This is just talking about the vibronic transitions, and that these intensities are approximated by the Frank-Condon factors, the overlap integrals of the ground state and upper state wave functions. So what does that mean? Well, this would be written out like this. Let's see. Let's say upper U for upper, and for ground state GS. What does that integral look like? It's two wave functions multiplied by each other and integrated over all space. Yeah, it looks very similar to the transition dipole. We're just not using the x-axis in the middle. And so we're saying, let's just forget about x in the middle, and let's just look at the overlap of the wave functions, and that will give us an approximation of the intensity of that transition. So this really works well, and this is, if you look at the shape of this ground state, it's a Gaussian shape. And so then if you look at the peaks up here, let me see, I'm gonna take this right here and I'm gonna move it down here and I'm gonna plot the spectrum. And I'm gonna draw a stick spectrum like this. So that's the Gaussian shape of the ground state, and you'll get, if you can resolve them, you'll get individual peaks like this, whose intensities kind of follow that Gaussian peak. So you'll have 5 different vibronic transitions, but their intensities kind of match this Gaussian ground state. And you'll see this in your iodine lab. It won't be as pretty as the nice, beautiful Gaussian shape, but you'll see the intensities of the peaks grow in and then go out. And then a whole nother transition will come in and go out. And so you'll see 3 overlapping transitions based upon the lower state wave functions. So you're going to be sort of peak picking and matching these peaks in the iodine spectrum. Anyway, the Frank-Condon factors are what are giving you those different intensities. All right, so now if we want to go from a diatomic, because all of these diagrams that we've shown are for diatomics, but not everything's a diatomic, obviously. So, yeah, like most everything's not a diatomic, right?
You said it's going to be 5 peaks, like 5 peaks, and like which case, all that.
Yeah, that's right. And so it gets so complicated that we don't draw these curves anymore. Okay, because it's, for a diatomic, you have one geometrical variable, the bond length. But for water or CO2, you've got 2 bond lengths and an angle. What are you going to do now? Okay, so that's why it's a surface. You have the bond length here, bond length there, maybe another axis of an angle, and you've got energy that depends upon all 3 of those. So it's a complicated surface. So we just bail on all of that, and we draw this Jablonski diagram. So what we have here is we've got the ground state. Okay, we've got the ground state, and I've just drawn a blue box here, and I've got these vibrational energy levels in this ground state, and that's going to be this whole thing over here on the Jablonski diagram. So it's just a rectangular block with a bunch of lines in it. Those lines represent the vibrational levels, and there's nothing important about the shape. It's just a vertical box that's filled with these vibrational levels. Okay, and then we'll draw maybe the triplet one or the singlet one. The singlet excited state would be drawn here, and we would label it singlet 0 for the ground state, singlet 1 for the first excited singlet state. We might have a S2, which would be the second singlet excited state, and so on. But we just draw a rectangle and fill it with little lines. We don't care how spaced the lines are. We just got a bunch of lines in there that represent the vibrational levels. And then if we hop from the singlet 1 to the singlet 0, that's internal conversion. That's what's meant by IC. And if we go from singlet 1 to triplet 1, that's intersystem crossing, which is what's meant by ISC. So then this triplet one would be this green box over here. filled with some vibrational levels. The only thing that's accurately portrayed in the Jablonski diagram is the minimums of these. So if you'll notice here, we've got 0. So the bottom of that box represents the ground state. If we do a spectroscopic measurement, let's say we get some fluorescence data from this particular system, then we could plot out the bottom of this triplet state at around 21,000 wave numbers. And then this one up here, if we did some fluorescence measurements, and we saw the singlet 1 to singlet 0 transition, we can see that might be like 31,000 wave numbers. And so these are the only accurate pieces of information. I'll say the minima. Does that make sense? Because we're not being accurate about the vibrational spacing. There's nothing important on the x-axis. We're just separating them for visual sake. So that's what I remember my college professor, he would say, he would draw the vertical axis as energy, and he called this NIP. And we said, what's that? He said, nothing in particular. Right? So we're just separating these boxes just for visual sake. And the only downside of that is, notice how our arrows look like they're going diagonal in this diagram. Well, this x-axis is no longer geometry. Okay, so we're over here, all of our absorption and fluorescence and phosphorescence arrows are vertical. We call those vertical transitions because this is the geometric axis. And with the speed of light, there's absolutely no way the molecule can change geometry, and like light can only go vertical because it's so fast that there's no time for the molecule's geometry to change. The vertical transitions in a potential energy surface diagram are vertical because light is so fast. It's the speed of light. So, this molecule is at a particular, atomic distance, bond length, and the electron cloud happens instantaneously. So those changes happen instantaneously. But when we go to the Jablonski diagram, the x-axis is no longer related to geometry at all. And so the arrows can be diagonal because there's no structural information on the x-axis. It's just sit there for visual. Yes.
So for how long, like the Jablonski diagram is, does that still count for like the strength of the bonds?
No.
Okay.
No. So there's nothing, no information on the horizontal part of this. It's just separated for visual effect.
Okay.
Yeah. So see, these overlap right here, but they don't in this one because there's we spread them out just to make sure we can see them separately. And so that's all. And there's no problem for S1 to S0. It looks like it's going through the T1. That's not going through anything. It can hop right over. So again, there's no important information on the x-axis of this energy level diagram. So this is kind of the pachinko game, the pump, the blue light. We're hitting the handle, and the balls are going up there, and this is what can happen. So we excite the molecule, singlet to singlet transition, and then you have the infrared heat, the radiationless relaxation through the vibrational manifold of the S1 state. And so that's non-radiative relaxation, distribution of energy along the vibrations of the excited state. And you have a little bit of infrared emission and collisional cooling. And then it could jump to the triplet state through intersystem crossing. So ISC, intersystem crossing. And it can rattle down through those energy levels, just like the pachinko game. Tink, 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 tink. It gets to the bottom and kind of gets stuck there. Okay. Yeah, and then it could spit out light using phosphorescence. Or it could do internal conversion and get all the way over to the ground singlet state and rattle its way all the way down to the very bottom and never emit any visible light at all. Okay, so here you're absorbing the light, and it's just heating up the substance. And the substance can cool down by emitting infrared light or colliding with its neighbors. So here it's absorbing light and heating up. And that's what happens most of the time. Not everything fluoresces, okay, or phosphoresces. And so you see this, and it could also do a second intersystem crossing here and come down. And so it can make its way to the ground state in almost every substance without emitting light. But certain substances are kind of rigid and they get stuck. And when they get stuck, emission is the last resort, and it'll spit out visible light. So visible light can come out in both phosphorescence or fluorescence. And if it's fluorescence, there's no change in multiplicity. And if it's phosphorescence, there is a change in multiplicity. So that's the Jablonski diagram. They don't have to be necessarily separated. Like you might see them, and I think I have one on the exam where the singlet is just a big box down here at the bottom. Okay. And so it can go straight down from singlet 1 to singlet 0, and that would be fluorescence. Or it could get over here to the triplet 1 and go down to the singlet 1, and that would be phosphorescence. But again, it's sort of showing the singlet 0 down below the singlet 1 and the triplet 1. So don't be confused by that. That would be another way to write the Jablonski diagram. Now, what causes all of this absorption? We call them chromophores. So, we use chromatic, chromaticity to talk about color. And so if you've got things that absorb visible light, it's going to produce a colored substance. We get into this a lot more in the forensic chemistry. There's 4 common chromophores that we deal with in different dyes and color change agents. We have azo dyes, we have carbonyl dyes, we have extended pi systems like beta carotene, and then we have what's the other one? Triaryl methynes. So a carbon that has 3 aromatic groups around it, and they're with steric hindrance. You can pull the proton off that carbon, so it's like a carbocation, and that's a very common color situation too. And nitro, you can put a nitro on aromatic. So nitroaromatics, those are different chromophores that cause absorptions in the visible region of the spectrum. These can be classified, and this is kind of a weak way to learn about the electron cloud because the visible spectral peaks are very broad. So you can't really learn much from lambda max. And so that's why I got into this colorimetry study. So y'all are doing the RGB lab this week, right? Okay. You're learning all about what I made. I made this cool little spreadsheet tool where I can model a molecule in Gaussian, and I can predict its wavelength of absorption and the intensity of that peak. And then I model the absorption spectrum here, and we know that absorption is proportional to concentration. So I can double that signal, quadruple it, multiply it by power of 10 or whatever. And so these are the multipliers over here, concentration factor, 1, 2, 4, 8, 16, 32, and so on. So these are the different absorption spectra that you get by artificially concentrating the molecule. I'm just taking the absorption spectrum, multiplying by 8 or 16 or 32. And then I'm converting every one of those over to transmission. And here's the transmission spectrum. And then I'm running these different transmission spectra through the RGB spreadsheet that you guys are building this week and coming up with the color. And so here's the RGB values for all of those spectra. And then I can calculate the chromaticity coordinates and plot it on this diagram. And so then I can get the color of the molecule. So I can take a Gaussian absorption spectrum and turn it into the molecular color of the molecule. And so this is azulene with the 2 aldehydes stuck on it, and it's a red compound. Okay, here's azulene with 1, and it's kind of a purple compound. And here's azulene, and you get blue. That's where the name azulene comes from, azul. Yeah, so this is a really cool tool that you can take a Gaussian calculation and figure out what the color of the molecule is. And it even works with the electron pushing, like the fluorines. You put fluorines on there, and it goes green.